unnecessary fear or misinformation about other dimensions. Challenges in proving parallel universes. Proving the existence of parallel universes is one of the most challenging tasks in modern science. The idea that our universe might be part of a larger multiverse, containing many other universes with different laws of physics, is a fascinating one. However, proving this concept is incredibly difficult due to several key challenges. First, one major challenge is that parallel universes, by their very nature, are beyond our direct observation. If there are other universes, they might be completely separate from ours, with no direct way to see or interact with them. This separation makes it hard to gather experiments or gather data from these other worlds. Our current scientific tools and methods are designed to explore and measure aspects of our own universe, not others that might be out there. Additionally, theories about parallel universes often involve complex mathematics and abstract concepts that are difficult to visualize or test. For example, string theory, which suggests that our universe might be one of many in a higher dimensional space, involves mathematical constructs that are challenging to represent in physical experiments. The higher dimensions proposed by string theory are not directly observable and remain largely theoretical. Another issue is that even if there were indirect evidence suggesting the existence of parallel universes, it would be hard to interpret. Scientists rely on observable. Moreover, the concept of parallel universes raises questions about how to test and falsify these theories. In science, a theory must be falsifiable, meaning it should be possible to prove it wrong through experiments or observations. The challenge with parallel universes is that if they are completely separate from our own, there might be no way to test them or disprove their existence. This makes it harder to validate or invalidate theories about them. Fechner's mystical and spiritual influence. Gustav Fechner, a German philosopher and physicist, is best known for his contributions to psychophysics, the study of how physical stimuli affect our senses. However, his work didn't just stay within the bounds of science. Fechner's interests extended deeply into mystical and spiritual realms. He was also fascinated by the idea that the material world might be hiding deeper spiritual truths. Fechner believed that the physical world we see is just a surface layer that covers a richer, more complex spiritual reality. This idea is sometimes described as seeing the physical universe as a veil obscuring hidden dimensions of existence. In his writings, Fechner explored the possibility that our everyday experiences might connect to a more profound spiritual order. One of Fechner's notable ideas was the concept of the soul of the world. He proposed that consciousness might not be limited to individual minds, but could be a universal or collective phenomenon. This idea suggests that everything in the universe might be connected by a shared consciousness, hinting at realms of experience that go beyond our normal work on space-time and consciousness. Roger Penrose, a renowned British mathematical physicist, has made significant contributions to our understanding of space-time and consciousness. His work is deeply influential and stretches across several complex areas of physics and philosophy. Let's explore his ideas in a straightforward manner. Penrose is best known for his work on the nature of space-time, particularly his development of the Penrose tiling and his singularity theorem. Penrose tiling involves creating patterns that cover a surface without repeating and without gaps. These patterns are non-periodic, meaning they don't repeat regularly like a checkerboard. This concept helps to understand the complexities of space and can hint at how space might be structured in higher dimensions. His singularity, This work helped explain why the universe started from such a dense, hot state and laid the groundwork for understanding black holes. Penrose has also explored the idea of consciousness. He challenges the view that consciousness is just a byproduct of brain activity. Instead, he suggests that consciousness might involve processes related to the fundamental structure of the universe. His theory, known as orchestrated objective reduction, or OR theory, proposes that consciousness arises from quantum effects in the brain. According to this theory, tiny structures within brain cells, called microtubules, may process information in a way that's not just classical, but also quantum. This means that our thoughts and awareness could be connected to the fundamental workings of the universe itself. Moreover, each universe evolves and collapses into a new one. Alan Guth and the theory of cosmic inflation. Alan Guth is a physicist best known for his work on the theory of cosmic inflation. This theory is crucial for understanding the early universe and has had a significant impact on cosmology. Cosmic inflation is a theory that explains how the universe expanded rapidly just after the Big Bang. Before this theory, scientists had a good understanding of how the universe expanded after the initial explosion, but they were puzzled about what happened during the very first moments. Guth's theory provides an answer to this mystery. According to the theory of cosmic inflation, the universe underwent an incredibly fast and enormous expansion during its first few moments. Keep blowing air into it, it expands quickly. In the same way, the universe expanded very quickly during inflation. This rapid expansion stretched out any initial irregularities or variations, smoothing out the universe and making it look consistent on large scales. One of the key aspects of Guth's theory is that it helps solve several problems that were difficult to explain with the traditional Big Bang model. For instance, it addresses the horizon problem, which questions why distant regions of the universe, which have never interacted with each other, have such similar properties. Inflation suggests that these regions were once much closer together before the rapid expansion, which helps explain their uniformity. Another problem is the flatness problem, which refers to why the universe appears so geometrically flat. Space could have stopped inflating at different times, leading to the formation of separate universes. These universes could have different properties and laws of physics, leading to a vast multiverse. Alan Guth's work on cosmic inflation has been supported by various observations and experiments. For example, the cosmic microwave background, CMB, radiation, which is the afterglow of the Big Bang, shows patterns that are consistent with predictions made by inflationary theory. This radiation provides a snapshot of the early universe, and its uniformity supports the idea that inflation occurred. Michio Kaku's contributions to string theory and the multiverse. Michio Kaku is a well-known theoretical physicist who has made significant contributions to our understanding of the universe. Protons, which are thought to be point-like and indivisible. However, string theory proposes a different idea. Instead of these particles being points, string theory suggests that they are actually tiny, vibrating strings. These strings can vibrate in different ways, and their vibrations create the particles we observe in nature. The different vibrations of these strings explain why we have different types of particles, like electrons and quarks, and why they have various properties. One of the key ideas of string theory is that the universe has more dimensions than the 4 we experience daily: 3 dimensions of space and 1 of time. According to string theory, there might be up to 10 or 11 dimensions in total. The extra dimensions are not visible to us because they are very small and compactified.